Okay, so I'm back for another video, and today I'm covering the delta epsilon definition of a limit. And so, if you've taken like high school calculus, you're probably familiar with the notion of a limit. And if you're not, this video might be really confusing. But anyway, like the standard definition is the limit as x approaches a of f of x equals like L, right? Or like C. Okay, so you have some function. You have some function. It looks like this, and at a specific point, as you approach that point from both sides of the function, it converges to some specific y value. So it converges to some L, right? So here's A, here's L. So the limit as x approaches A from the left and the right, as it converges to this A, as the distance in between like the left and the right approaches 0. If you're familiar with like the limit definition of a limit, so limit as h goes to 0 of f of x plus h minus f of x over h. So as this distance goes to 0, you approach some limit. So this is the standard notion of a limit, right? But if you want to get more rigorous, there's the epsilon delta or delta epsilon definition of a limit. And the statement is, so for all epsilon greater than 0, there exists some delta greater than 0 such that if 0 is less than the absolute value of x minus a is less than delta, then f of x minus L is less than epsilon. So this looks probably very confusing if you've never seen it before. You probably have no idea what the hell I'm talking about. So let's break it down. So we have some variable, epsilon, right? And we know that for all epsilon greater than 0, there's this other variable, delta. And so we can think about this. You probably think I'm crazy if you've never seen this before. But let's say we have that same like function like this. We have that same limit at 2, right? And so at 2, f of x takes on this value here. We'll just assume f of x is continuous, right? So it takes on this value, this L. And so traditionally, we have like f of x converging to this limit. But now we define some epsilon and delta. And so epsilon is, or first we'll go with delta. Delta is like a delta neighborhood. You can think of it as like a super small neighborhood around this x value. So you see this 2? Delta is a very small neighborhood. Like it's not drawn to scale, but this would be a very like small neighborhood, like as small as we want, around 2. So this boundary would be 2 plus delta and 2 minus delta. And then epsilon is the same, but just for the y-axis, okay? So we have this, and then we have L plus epsilon and L minus epsilon. So pretty much what this is saying, like graphically, is if we constrict like our point here to some delta neighborhood on the x-axis, our output is restricted by some epsilon neighborhood on the y-axis. So as f of x approaches this limit on the x-axis, as this neighborhood gets very small, we can control delta, but as this gets very small, the output is also small. And so this guarantees that as we get closer and closer, as we approach, as the distance from both sides converges to this point and it approaches 0, this epsilon neighbor is also contained, and so our output is also very close to this limit. So if the absolute value of x minus a, if the difference from x and a is less than delta, so a is the point we're approaching, a is this 2 here, this is a. So as the distance gets very small in between here, the distance between our limit and the actual value of f of x also gets very small. It's less than some epsilon greater than 0. And so I think it'll make more sense if we do like an actual concrete example. So let's take, I haven't thought of this. Let's take the function y equals 2x, right? So if we draw y equals 2x, it looks like this, right? And then let's take the point, let's let a equal 3, right? I'm gonna move over here. So if we have the limit as x or let's do 2. You want 2 or 3? We'll do 2. Okay, we'll do 2. The limit is x approaches 2 of 2x. I think we all know if you just plug in 2. Well, if you're not familiar with calculus, you don't know, sorry. But if you are, you know that this is 4, right? So this is 4. So if we concretely just look at this, f of x is 2x, L is 4. So if we just plug this directly into the definition, what this is saying is if 0 is less than the absolute value of, or is, if this is greater than 0, x minus 2 is a is 2. If this is less than delta, then f of x, which is 2x, 2x minus L, 4, is less than some epsilon. Less than epsilon. Okay. So how you go about doing these delta epsilon proofs is you need to prove that this is true to prove that this limit is actually true. So first you guess what the limit is, and then you guess what delta is. It's a little convoluted, but typically you do some like scratch work off screen and you like then assert what delta is. And here I know that delta is going to be, we let epsilon equal delta over 2. Because how this works out is, here, we'll do it here. So 2x minus 4 is the same as 2 times the absolute value of x minus 2. And this is actually our delta, right? So this is our delta, and we know that this is less than delta. So if we let epsilon equal delta over 2, or sorry, if we let delta equal epsilon over 2, then we know that this is true. So yeah.